other types of equations. And this is we start off with the other method of solving an equation graphically. This first one, you say, this equation is so simple. It's a linear equation. Why would you want to take the time to solve this graphically? And I think it's simply because it's linear, the two graphs that we're looking at are straight lines, so it's very easy to see where they intersect if neither one of them is very steep. So let's see if we can graph this and use the intersection of graphs method. Now with the x-intercept method that I just showcased at the end of that last section, you get 0 on one side, and you just have one graph. Y equals the expression that you have on the other side. And you use the 0 feature, and you find where the graph intersects the x-axis. In the intersection of graphs method, you don't have to get 0 on one side. You just graph y1 equals the left-hand side, and you graph y2 equals the right-hand side. Don't even have to simplify it if you would prefer not to, because you run the risk of, I don't know, you're probably not going to make a careless mistake in simplifying, distributing the -2 across the parentheses there. But it's not even necessary to simplify that. Just type y equals the left-hand side, y equals the right-hand side, and then we'll graph these and look for a value of x that gives these two expressions the same value. If we find a value of x that gives these two expressions the same value, it'll be a point that they have in common, because it'll be the same value of x and the common value of y. Let's graph both of these. Y equals the left-hand side, -3x plus 1. And we'll graph the other one. Y equals -2. Parentheses above the 8 and the 9. So 4x plus 2. Y equals the left-hand side. Y equals the right-hand side. Now, the viewing window that we had previously is probably not a good one for this example. I don't know what it would look like. Probably not good. Now, that's kind of tough to see what's going on with that viewing window. The standard viewing window is a good place to start for a lot of the examples. Not all the examples that we do, but for a lot of the examples, the standard viewing window. So I'm going to press zoom at the top middle, press zoom, and then number 6 on the list is zoom standard. It will automatically press this. I'll go ahead and press it, enter. It automatically resets the x min to -10 and the x max to +10 and the y min to -10 and the y max to +10 and the x scale to 1 unit. So when you look at the little tick marks, that's 1, 2, 3, 4, 5, 6 all the way to 10. And notice they're a little bit closer together along the y-axis just because it's a rectangular viewing window, not a square viewing window. And to squeeze 20 of them in between y equals -10 and y equals 20, so y equals -10 and y equals +10, there's less space. So they have to be closer together. It looks like they intersect at this point. Let's get the calculator to tell us the coordinates of that point. We can do that using second calc. What do you think? Intersect. Second calc intersect is what we want. So we press 5, or simply enter second calc 5. Now, instead of a left bound and a right bound, it's going to ask first curve. If I successfully give it a first curve, it'll ask for a second curve. If I successfully give it a second curve, it will ask for a guess. Now, it asks for first curve and second curve because there are situations where there might be more than 2. And it needs to know which 2 out of the many graphs that are up there do we want it to find the point of intersection of. Now, it simplifies things considerably if we only give it 2 curves to choose from. If that's the case, we just press enter for the first curve. Now, provided right in the middle of the screen happens to be in the domain of that expression. We'll talk more about domain later. Here, they're both linear and no restrictions on their domains. Sometimes there are issues. It's slightly more, how to say it, slightly less trivial than this to tell it the first curve and tell it the second curve, but it's not difficult in this case. Just enter, enter, and it's got a first curve and a second curve. Now it wants a guess. Now, it's 2 straight lines. If they have different slopes, they will intersect in exactly 1 point. So it's going to be easy enough for the calculator to find the point of intersection. If we had a straight line and maybe something curvy, they might intersect in more than 1 point. And if that were the case, what we'd have to do is choose which one we want the calculator to find first. And so what we would do is scoot the cursor over closer to the one we want to find first and press enter, and it'll find it. And then repeat the process. Scoot it down to the other one, it'll find the other one. Here, there's just the one. So I'll press the left arrow just a couple times, press enter, it searches, and it finds -1,4 as the point of intersection. So there it is, -1,4. So I would suggest that you take that and copy that onto your page with pencil and paper or whatever you have to work with. Yes?
When you put in a guess, what did you move it to?
I just pressed the left arrow 2 or 3 times. Second calc 5, enter, enter. Well, I guess it was there. I probably moved it to about -1.06 something like that. But I just used pressed the left arrow 2 or 3 times, and it got me there. So we got this picture. Now the two curves, the one that's steeper, if I had simplified the right-hand side, that would have been -8x minus 4. The one that's steeper is the one whose slope has the greater absolute value. So that's this one right here is your y2 is -2 times 4x plus 2. The one that's not so steep is the y1, -3x plus 1. If we substitute -1 for x in our y1, -3 times -1 is +3, and 3 plus 1 is 4. It makes the left-hand side equal to 4. If we substitute -1 into the right-hand side, 4 times -1 is -4. -4 plus 2 is -2. And -2 times -2 is +4. So it makes the right-hand side equal to +4. Now there's something very important about the way you want to express your final answer to this problem. Because you do everything right. You graph y equals the left-hand side, you graph y equals the right-hand side, and you even indicate that the point of intersection is -1,4. You do all that, but what you don't want to do when expressing your final answer is this. You don't want to say that the solution set is that. Wait, you wouldn't put +1 anyway, would you? You don't want to say the solution set is that. What's wrong with saying the point -1,4 is the solution to this equation? You're looking for the x value. It's not a point on the graph, it's a number that can be substituted for x that makes both sides equal to the same number. Now that number happens to be 4. If we were to check our answer, plug in -1 for x over here, -1 for x over there, we get 4 on both sides, and what we need is the fact that 4 equals 4. But 4 is not part of the solution set, so what you do want to do is that. You use the calculator and you come up with this point of intersection, and then you look at the point of intersection and you realize that the solution is right there. That's the solution to the equation, not the entire point. So you punch buttons on the calculator, but then you have to interpret what the calculator gives you and figure out, okay, I was looking for the solution to the equation, there it is, -1. Questions about that? Yes, sir.
On the test, will there be a problem like this where you have to use a calculator, or is it like
right? There will be. There will be at least one, maybe a couple of problems like this where you need to use a calculator, and it will make it a little uglier than this. So you wouldn't want just. I mean, this is a fairly trivial linear equation to solve without the use of the calculator. So we'll throw in some radicals and mess it up a little bit. And part of the challenge will be to take those expressions and type them correctly into the calculator and then interpret the results. But there will be at least one, I think throughout the semester, probably 3 or 4 graphing calculator-oriented problems like this. Yes?
Will you have a do we get a chance to practice these kinds of things in the textbook or on Alex? Or can you recommend a page?
There's
where we
not,
can go
yes.
practice?
I really, there exists a fairly nice handout on this that I probably need to give you or link to it or something like that. Unfortunately, Alex has a good problem, but it doesn't happen until section 4.5, which we won't get to till December. It involves exponential equations and logarithmic equations, and it's good. It'll generate as many versions of it. I might be able to create a GeoGebra worksheet that what it could do is you could click on it and it'll give you a kind of a randomly generated sample problem, and then you type it in your calculator and you type it in and see if, and you kind of compare to what it gives you, and that gives me a good idea. I haven't done it before because my math lab, when we used my math lab back in the good old days, it had a couple. I was able to design a problem for use with my math lab where it gave students practice doing that very thing. And there's really not a good Alex problem. So I'm going to have to try kind of an end around and get something so you can, because you need practice. You need to be able to work this 10 times in a row until you know I've got this. Just watching me do this and then showing up to try it on the test, that's not good enough. So thank you for that. I'll put it on my mental to-do list and hopefully actually get it on my physical to-do list soon after class dismisses. Let's see. There's another practice problem. Let's see if we can do it with an uglier one, though. Example 2. Right there. Solve the following equation using the intersection of graphs method. Round your answer to the nearest thousandth. 3 decimal places is what we're looking for here. Not going to simplify either side. If you're typing these using the TI-83 plus, you're going to want to type y1 equals 9 times, be sure and use the negative sign rather than the minus. If you use the minus, you will get a syntax error. Be sure you leave that expression with a negative sign. 0.84x plus, and on the TI-83 plus, you press the second x squared where the radical is, and you get this, and you type a 17 inside, and then you close the parentheses for the square root of 17, and then you close the parentheses again for the actual parentheses that appear on the left-hand side. For the right-hand side, y2 equals, now this one's tricky because it's not the square root of 6x, it's the square root of 6 times x. And it's important to get the notation just right. So the square root of 6, the key thing there is to close the parentheses after the 6, so it stops taking the square root right there. And then you can type the x and then the minus 4. Now if you're using the TI-84 plus, it's going to look pretty much like what you see on the screen. Yep, sorry about that. Let's go here and then there. That's what I want. So it's going to be y equals 9 times negative 0.84 x plus the square root of 17. Key there is press the right arrow to get out from underneath the radical sign, and then close the parentheses. So that entire expression inside the parentheses gets multiplied by the 9. Then down, second square root. Go ahead and type the square root of 6, and then be very careful to get out from underneath the radical sign. So it's the square root of 6 times the x minus the 4. This should be 2 straight lines. They're not nearly as nice looking straight lines or nice expressions to define those straight lines. But the one on the left has a slope of whatever 9 times negative 0.84 is, maybe negative 7 or 8, something like that. And the one on the right has a slope of positive the square root of 6. But they're both straight lines, and hopefully they intersect in the standard viewing window. Let's see. Zoom. 6. Now, I was in the standard viewing window, so really all I would have had to do was press graph. So if you press graph, it should display this, but since I'm there, zoom 6. Not seeing much. There's the one. Okay, well this is too easy because the point of intersection is actually in the standard viewing window. I would like you to be able to solve a problem like this where the point of intersection is maybe not in the standard viewing window. So I'll do this one and then tweak it just a little bit and change it up. Second calc 5, and then first curve, enter. Second curve, press enter. Just two curves there. It's easy for the calculator to find both of them. And for a guess, honestly, you can use just about anything for the guess here, since they only intersect in the one point. If you want to move the cursor closer to the point of intersection, give the calculator an easier way to go, feel free to do so. Press enter. So on my paper, I'd want to put something that looks like this. You don't have to scribble the numbers at the bottom. I would like you to label the point of intersection, though. 4.107, 6.0, whoa, what is it, 60? 60, like that. Label the point of intersection, but report your final answer is just the x-coordinate. Oh.
When I type in the calculator, I'll type in the equation and the calculator and graph it. I get a comfortable graph and numbers.
Does the graph looks different?
Yeah.
I probably need to come and look at that. Let me go ahead and put 4.107 as the solution there, and let me take a quick look at that because I like it when you get home or wherever you're going to work on this, that we're all pretty comfortable with the process. What if the point of intersection is not in the standard viewing window? There may be an upcoming example that'll give me an opportunity to demonstrate that. Let's see. Let's do example 3A. There we go. Sample 3A, let's type these in and see. I would suggest using the pi on your calculator if we want, well, it's 2 decimal places here. If we want 2 decimal places, we might be able to get by with 3.14. Might be better to have a little bit more accuracy with the way we express pi, a little bit more precision with accuracy. So I'm just going to use the pi button on the calculator. It's on the exponentiation or caret button right here above the divided by. You press second and then that button, y equals, I'm using the clear to clear the expressions in the y1 and y2. If you press clear, it clears them faster than delete will. So second pi, then the x minus, open parenthesis, 1 minus the square root of 2, out from underneath the radical sign, or close the parentheses, times x, and then close the parentheses. There is y equals the left-hand side. For y equals the right-hand side, negative square root of 0.25, and the pi is also underneath the radical sign. So the slope of that line, the one on the right-hand side, is negative the square root of 0.25 pi. Multiply that. Am I out from underneath the radical sign? No. Press the right arrow to get out from underneath the radical sign. Then press x, and then plus 5. One more time, zoom 6. It's going to disappoint me a little bit if the point of intersection is obviously in the standard viewing window. And I'm disappointed. Let's see a way I can tweak this. I'd like to be able to see both lines, but not necessarily see where they intersect. Let me do this. For the second, the one with the positive slopes, actually the first one, if I could tweak that just a little bit, change the sign of its slope. Right now it's positive. I can go. Let's do this. I'm just going to change the problem because I want to be able to illustrate. I don't advise this on a test. On the test, you should go with the problem that's there, whatever's there. But I'm going to exercise some license or privilege or whatever it is, and I'm going to do that and that. And I don't know if that's going to do exactly what I want it to do, but if it doesn't, I'll fix it some more. So I'm just going to second insert, second button followed by the delete button will enable you to insert a negative sign in front of that pi. And then changing that minus to a plus, you can just scoot over and overwrite that minus and make that a plus. I believe that fixes it. It's going to change it from a positive to negative slope. It's also going to change some other things I might not have wanted to change. Let's see how it works out. Not exactly what I was going for. What I was wanting, how can I fix that? I suppose I could subtract. I could subtract about 40 from it. Let's do that. Maybe put a negative 40 in front. Y equals insert negative 40. And now, since that minus, that negative sign in front of the pi is now in the middle of the expression instead of the front, it needs to be a minus instead of a negative sign. So negative 40 minus pi x plus that quantity 1 minus the square root of 2 times x. Graph. Is this finally going to do what I want it to do? I think maybe so. Yeah. This is exactly what I wanted it to do. So this is the official problem now that we're working on. To solve this, we need the point of intersection. Now, if we just say second calc 5, first curve enter, second curve enter, guess, I think the arrow is something like no sign change. Yes, no sign change. Basically, it's subtracting one of them from the other, and it's not getting the sign to change inside the viewing window. So what we need is to modify the viewing window. Second quit. What suggested modification would you make to the viewing window so that we can find, so the point of intersection will be in the viewing window? What do you think? It's not between negative 10 and 10. Is it to the left of where we're looking, or is it to the right of where we're looking? What do you think? It's like probably up here somewhere, right? It's to the left. So instead of negative 10 for x min, maybe negative what? 20? All right, so negative 20. Now, we could change the y max also, just so we could see the point, but that's not as crucial. The point itself doesn't have to be on our view screen in order to find the point of intersection. At least I don't think so. I should probably confirm that. It's still above the view screen. It just has to be in between, the x-coordinate of the point, has to be in between the x-min and x-max. And then it should be able to do what it does and find the point of intersection. Let's see if I'm right about that. It's been a while since I've done one of these. Second calc 5. First curve enter. Second curve enter. Fingers crossed. It found it. We can't see it because it's above the view screen up here somewhere. But negative 11.99, 15.63 is the point of intersection. If we wanted to see it, we would need a greater y max. Let's go with 20 for the y max. And then have the calculator redo it. Second calc 5, enter, enter, enter. And then we've got it. Probably you want this because you want to copy this onto your paper. And so we've got negative 11.99. If we want 2 decimal places, 15.63. But the solution to 2 decimal places is what? There we go. Good. Negative 11.99. Let me take some inventory here and see where we're going. B part and the C part. I'll probably do the C part next time because it's quadratic, 2 points of intersection, and we'll need to see that we do those one at a time. So I think that's a reasonable thing to do. The x-intercept method, probably just one of those because we've already done one of those. We did that with the projectile motion, the mortar, finding out the time when it hit the ground. So it won't take us long to get to example 5 next time. So that's kind of where we'll pick up. So example 3, use your calculator to find all solutions to 2 decimal places to the equations. Up to this point, we've been working on the using the intersection of graphs method, which in a lot of respects is simpler than the x-intercept method. We don't have to worry about the left bound and the right bound to come up with the x-intercepts, but we also want to consider how to do this with the intersection of graphs method as well. So get everything warmed up here. What we want to do is on the calculator press the y equals button and type in y. Well, you've got the y1 equals. We want to graph y equals the left-hand side of this equation, and we want to graph y equals the right-hand side of this equation. And we want to look for the points that they have in common because the x-coordinates of those points will be the solutions to this equation. So y equals the left-hand side, the y equals button in the upper left, xt theta n button to display the independent variable x. You can use the exponentiation button or just press the x squared after you press the xt theta n button, and it will square it for you. Minus x minus 15. So that'll give us a way to relate the values of the left-hand side in terms of x. We want to consider the values of the right-hand side in terms of x. So 3x, I didn't mean to do that. 3x minus 1 for the other one. We'll graph both of these. The first one will be a parabola. Should be able to recognize that one. The second one, a straight line. And I'm going to begin in the standard viewing window. Now, if you know your calculator's in the standard viewing window, all you have to do is press graph. You don't have to zoom anything. But if you're not sure where that viewing window was, when last you left it, might be a good idea to zoom 6. So press the zoom button, followed by, well, come on, zoom button, there we go, followed by the number 6. There we go. Zoom standard. Automatically sets the x-min to -10, the x-max to +10, the y-min to -10, the y-max to +10, and it puts a tick mark on both the x and y axes every 1 unit. Okay, not bad. I'm thinking there are probably 2 points of intersection here, and we see the one right here down the third quadrant. I believe there's another one up in the first quadrant, but it's above the screen. Now the calculator will still find it if it's above the screen. I think we mentioned last time, it won't find it if it's to the left or to the right of the screen. But if it's above or below the screen, it will find it. Nonetheless, I'd like to see what it is, and I want to know what graph I want to scribble onto my paper if I'm putting this on a test. So y min, what, negative 20, would that be low enough, you think? Really don't have to go any lower. We saw the point there. But I want to see the bottom of that parabola. Y max, let's go to 30 and a y scale of 10. Just kind of feeling my way through this. I know it needs to go higher because there's a point above the screen that I want to see. So I changed the y max from 10 up to 30. And now from a y min of -20 to a y max of 30, there are going to be 50 tick marks up and down unless I change the y scale to 10. It was 1. If I change it to 10, then it'll be -20, -10, 0, 10, 20, 30, and there'll be a good amount of space between them. Not too much, but certainly not too little. Graph it. That's a little better. Looking at this, we see 2 points of intersection. So if I just wanted to give a rough idea, maybe to the nearest whole number, maybe to the nearest tenth of each solution, the x-coordinate at this point looks like it's negative 2 point something. Maybe I'd call it negative 2.2. So if I were to evaluate the left-hand side, if I took a negative 2.2 and substituted for x on the left-hand side, it would give me about negative, what's my y scale? 10, negative 8, something like that. And if I plugged in that same number on the right side, it would also give me about negative 8 or so. So since it makes both sides equal to the same number, we call it a solution to the equation. Likewise, up here, I'm thinking it's about, 6 point something? Maybe 6.2, 6.3, something like that. If I'm reading that correctly. It might be 5 point something. 1, 2, 3, 4, 5. No, 6 point something looks better. 6.2, we'll call it. If I plug in 6.2 to both sides, it makes the left-hand side equal to about, 18? And it makes the right-hand side about 18. So it makes the equation true. It makes both sides equal to the same number. Now, let's have the calculator be a lot more precise without losing any accuracy. Second button, calculate up on the trace button, second trace or second calc to get there. Number 5 on the list, we're looking for points where the graphs intersect. We have to find them one at a time. Enter. Now, there are only 2 curves there. We talked about sometimes there might be more than 2, but probably not in this class. Probably we'll keep it just to 2 curves. So quickly you can press enter to select the first curve. It jumps to the second one and suggests that this is a nice looking curve. Why not this one? Well, we say okay. We press enter. And then for a guess, move the cursor. You can either type in the x coordinate of the point that you want to find, or something close to it, or you can move the cursor left and right using the left and right arrows. So we could go left, 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 left. And it does look like about negative 2 point something. Press enter, and the calculator searches and finds, not bad, negative 2.24. How many decimal places? 2 decimal places. Negative 2.24 is what we want if we're going 2 decimal places. So I would take and scribble this picture onto my paper, label the point as negative 2.24, negative 7.73, and I know that a solution, an approximate solution to this equation is negative 2.24. If I'm going to take a number and round it to 2 decimal places, evaluate the left-hand side, evaluate the right-hand side, that number, negative 2.24, is going to make the 2 sides closer to each other than any other number in that vicinity rounded to 2 decimal places. We'll see what this one up here does. So repeat the process. They're both typed in. We don't have to repeat that. We just have to repeat second, calc 5, first curve enter, second curve enter. And then for a guess, you could press the right arrow a whole bunch of times. If you're sick of pressing the right arrow, you don't want to do that. You can say, it's about 6 point something, so just type 6. Let that be your guess. Give the calculator a starting point. So if there are 2 solutions and one's closer to 6 than the other one is, it should find the one that's closer to 6. So you type 6, you press enter, and it gives 6.24. 17.73, 6.24, 17.73, which means if we take 6.24 and plug it in for x on the left-hand side, we get about 17.73. And if we plug it in for x on the right-hand side, we get about 17.73. So it makes it a true statement. So the other solution is 6.24. The big key here is we don't want to include the negative 7.73 and the 17.73 in the solution set. That means we're not quite sure what's going on here. We've got an equation with one variable. We want to find numbers that can be substituted for that variable to make it true. And these are the ones. Negative 2.24, 6.24, The negative 7.73 and the 17.73 are not solutions. They're just what we get on both sides that agree with each other that tells us, oh, it makes the equation true. This is a hard problem or an easy problem? What do you think? An easy problem. Once you've got the calculator figured out, this is a pretty easy problem. Little learning curve to get there, but once you're there, it's not bad. Press the right button. Oh, I want to do the same one using the x-intercept method. So the details of the x-intercept method are found in the notes. So the x-intercept method, and a little bit more in the way of details as well. Let's go with this. And then let's solve this equation again, rather than the one that's mentioned in example 4. I just want to compare the two graphs. So suppose we've got x squared minus x minus 15 equals 3x minus 1. And the mood just doesn't strike us right to use the intersection of graphs method, and we'd like to use the x-intercept method instead. Now the x-intercept method requires that we, where does it say here? Some point somewhere we need to get 0 on one side. Obtain a 0 on the right side. So let's do that. Let's subtract 3x from both sides and add 1 to both sides so that we have x squared minus 4x minus 14 equals 0. Check and make sure that I did that right. Hopefully that's good. X squared minus 4x minus 14 equals 0. Now, for the moment, you could kind of think, well, we could use the intersection of graphs method. We just graph y equals the left-hand side and y equals the right-hand side and see where the two intersect. But y equals the right-hand side, y equals 0. If we graph y equals 0, what graph do we get? What line is y equals 0? What is that? What do we call it? It's the x-axis, right? It's the straight line, horizontal line, all of whose y coordinates are equal to 0. It's the x-axis. So what we're really trying to find is the points where y equals x squared minus 4x minus 14 intersects the x-axis. Now, we could do it the same way if we actually type in y equals 0 to the calculator, and you might ask, well, why not just do that? Well, it's an extra thing to do, and that's the only reason not to do it. Otherwise, you'd just do that. Or we can take y equals x squared minus 4x minus 14 and find the x-intercepts without actually typing y equals 0 into the calculator. So tweak this just a little bit, change it to y equals x squared minus 4x minus 14. And I'm going to use the clear button on the 3x minus 1. You can delete, 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 delete if you'd prefer, or just press clear for the 3x minus 1. Now, if we graph this, it's probably going to look a whole lot like the other parabola that we had. Except in this case, we're not looking for where this parabola intersects a slanted line. We're looking for where this parabola intersects the x-axis. And the procedure is a little different. Instead of using the second calc 5 intersect feature, it's going to be second calc 2, I believe, looking for the zeros of this expression, the numbers that can be substituted for x to make this expression equal to 0. So second calc, number 2 on the list, second trace for second calc, and then number 2 on the list, 0. Now, instead of first curve and second curve, there's only one curve here. So it doesn't need to ask us first curve, second curve. If there were multiple curves, we'd probably need to indicate which curve we're working on. But it asks us for a left bound. It asks us for a, if we give it a left bound successfully, it's going to ask for a right bound. And if we give it a right bound successfully, it will ask us for a guess. So I'm going to press the left arrow. What we want to tell it, we've had to find these zeros, these x-intercepts, one at a time. And so we have to decide which one we want to find first. I want to find this one on the left first. So we have to tell it the endpoints of an interval within which it can search to find the 0, to find the x-intercept. So basically, sorry about that, it disappeared. Basically, I'm telling it looks like it's negative 2 point something. So I'm going to click a little to the left of negative 2 point something, maybe negative 3 point something. And then I'm going to press the right arrow and click a little to the right of negative 2 point something. How about negative 1 point something? There we go. And basically, for the guess, I'll press the left arrow a few times to get kind of close to the x-axis and have the calculator start here and search throughout this little interval from negative 3 point something to negative 1 point something to find the value of x that makes the value of this expression as close to 0 as possible. And it does a pretty good job of doing that in general, so it's going to give us a value of x that makes this thing really close to 0. So it searches and it finds negative 2.242641. And we can trust probably most of these decimal places. I think this one, I guess I didn't copy the instructions there, but 2 decimal places are probably good. So negative 2.24, I think was one of the solutions we got before. So what we'd want is to scribble this graph onto the paper and label this x-intercept negative 2.24 comma 0. And there's another one over here. Repeat the process. Second calc, number 2 on the list. Now it's way over there to the right, so maybe instead of pressing the right arrow multiple times to get over there, just look at it and say it looks like it's 1, 2, 3, 4, 5, 6 point something. So if we wanted to use maybe 5 as a left bound, that would work nicely. 6 would also work nicely. And then maybe 8 as a right bound. 8, enter. 7 would also work nicely, but 5 and 8 a little bit farther apart. And then for a guess, I think it's 6 point something, so I'm just going to guess 6. Just type in the number 6 and press enter, and it searches and it finds 6.24. So on the graph, label 6.24 comma 0. So we've got these 2 intercepts, and all we want are the x coordinates, negative 2.24, 6.24. To 2 decimal places, these are the numbers that make this expression as close to 0 as it could possibly be. Yes?
Is there a situation where you have to use like the x-intercept and like where you couldn't use the intersection graph method?
Not really to my knowledge. There are some situations where one of them just seems more natural than the other. Studying polynomials in pre-calculus, you've got a polynomial function, or any type of function. It's just a matter of finding the zeros of that function. There's really not another side other than 0, and so it's very natural to want to use the x-intercept method to do that. On the other hand, if there are 2 graphs and they both have some particular significance, and there's also some intrinsic significance to the point where they intersect, the intersection of graphs method may also be, if it's maybe a profit function or a revenue function, a cost function, you're looking for a break-even point, there might be some real significance to the y coordinate as well. So you might not want to get 0 on one side. You might want to really call attention to the point where they intersect. So there are good reasons to do both, but there's not a situation where if you weren't comfortable with one of them, you couldn't get by with the other one. Okay, let's move our attention away from the calculator and look at some basic techniques for solving rational equations and radical equations. There's several of these. I'm going to skip a little bit and go ahead and look at example 6. Example 5 involved a proportion. There are multiple ways of solving that. One could simply cross-multiply, but cross-multiplying will only take you so far. A more general method that we'll look at in example 6 involves getting rid of the fractions by finding the least common denominator and multiplying both sides by the least common denominator. So we want to make sure we've got all the denominators where we can see the factors clearly, so we really do find the least common denominator. If we go with a denominator that's too big, we can make this a real mess. So 15 over x plus 3 times x minus 2 plus 3 over x minus 2 equals 2 over x plus 3. Just factoring that first denominator, just to see if it had anything in common with the other two denominators, and it has everything in common with the other two denominators. So if I'm looking for the least common multiple of x plus 3 times x minus 2 and x minus 2 and x plus 3, certainly we've got to have a factor of x plus 3. And certainly we've got to have a factor of x minus 2. But if we have those two, that's enough. Everything's covered. That's divisible by x plus 3 times x minus 2 because it's equal to it. It's divisible by x minus 2 because that's one of the factors. It's divisible by x plus 3 because that's one of the factors. So if we just multiply both sides by x plus 3 times x minus 2, it will eliminate all the factors and all the denominators, and we'll have ourselves a polynomial equation, which we can attack probably by factoring or maybe the quadratic formula, worst case scenario. One thing before we jump into this is the matter of domain. Once we multiply both sides by x plus 3 times x minus 2, we won't have these factors with x's in them in the denominator anymore. So the domain of the new equation will look like it's potentially greater than the domain of the original. We want to make sure that these numbers that make the denominator 0 don't inadvertently wind up in our final solution set. So what number can you substitute for x right there that makes x minus 2 equal to 0? 2. So 2 is bad. 2 is not in the domain of this expression. So it's not in the domain of the equation, and if it shows up in the solution set, we'll have to disregard it. Sometimes that happens. We do all the right things, but still end up with a number that doesn't quite satisfy the original equation. So x equals 2 is bad. So kind of as a domain restriction, we want to say x is not allowed to be 2. And what's the other bad value of x? Negative 3. X is not allowed to be negative 3. So we just kind of keep that in the back of our mind or off in the margin somewhere. Might not even come into play. We might get 5 and 6 as the two solutions to this, or maybe just one solution that's not equal to either one of these. But if it happens to be one of these, and sometimes it does happen, we've got to make sure that we exclude them. Now, a big step that I'm tempted to skip, I don't think I will skip it, but a big step is where we actually multiply both sides by x plus 3 times x minus 2, because it looks like a lot to write. Multiply by, too dark blue there, multiply by 15 over x plus 3 times x minus 2. And then over here, we're going to take x plus 3 times x minus 2 and multiply by the entire right-hand side. Whoa. There's more on the left-hand side. Sorry about that. Let's see if I can capture just this portion of it and scoot it over. I left off, so sorry about that. I left off the plus 3 over x minus 2. There, that's better. So the entire left-hand side gets multiplied by x plus 3 times x minus 2. And the right-hand side don't need nearly as much space inside there now. There we go. Gets multiplied by x plus 3 times x minus 2. Sometimes that's just what we need to do when we're solving an equation. Find some factor or product of factors and multiply both sides by that same quantity, as long as we're not multiplying both sides by 0, and if x is in the domain, we're not going to be multiplying both sides by 0. We get an equivalent equation. Now on the right, we can actually go ahead and start scratching some x plus 3's. The idea is to be able to scratch out this x plus 3 with that x plus 3. And because there's only the one fraction inside the parentheses, we can go ahead and do that. And on the right, we're going to have, I'm going to scoot that over because I know I'm going to need lots of space. Whatever remains when the dust settles, it looks like x minus 2 times 2, or 2 times the quantity x minus 2. On the left, it's going to be very dangerous if we go scratching x plus 3's and x minus 2's, because if I were to do that, say scratch that x plus 3 with that x plus 3 and scratch that x minus 2 with that x minus 2, well, there are a couple of issues. Number one, we probably would notice because all of a sudden there's nothing left to scratch out that x minus 2, and we're going to be missing a factor of x minus 3 that should have wound up next to that 3. So let's take the left-hand side through an extra step where I write out what's about to happen by distributing the x plus 3 times x minus 2 across those parentheses. So it's looking like this. The x plus 3 times the x minus 2 gets multiplied by 15 over x plus 3 times x minus 2, and the x plus 3 times x minus 2, according to the distributive property, also gets multiplied by the 3 over the x minus 2, and then we add those two resulting products together. Is that clear what's about to happen there? Taking that product, x plus 3 times x minus 2, and distributing it across the left-hand side. So we do that, and now, since we have extra copies, as many copies as we need of the x plus 3 times x minus 2, we can go scratching them out. Divide by x plus 3, divide by x plus 3. We can do that, of course, because you can think of x plus 3 times x minus 2 as being over 1. So we've got factors in the numerator of a fraction, factors in the denominator of a fraction. We know we multiply fractions. We can divide out common factors, numerator to denominator. So we divide out those. We divide out the x minus 2's. And if we want to think of this one as being over 1 as well, we can divide out those x minus 2's also. So the whole point of doing this, it looks like it makes a big mess, but we want an equivalent equation without all those fractions. So when the dust settles, there won't be any fractions. What we'll have is 15 plus 3 times the quantity x plus 3 equals 2 times the quantity x minus 2. And certainly we could have distributed the 2 across the parentheses. I know we'll at the next step. Just don't want to get too far ahead of the left-hand side. So far, so good? Okay, so just copying it so it shows up in the next page. Simplify. A couple of steps, simplify the left-hand side. 15 plus 3x plus 9 equals 2x minus 4. 3x plus 24 equals 2x minus 4. We're almost there, but at this stage in the process, I always like to stop and ask, once the fractions are gone, once the parentheses are cleared, once the like terms have been combined, I like to ask, is it linear or is it quadratic? It is linear, because there's two different ways to go. If it's linear, we isolate the x term on the left-hand side. And if it's quadratic, we probably want to get 0 on one side. So different approaches depending on whether it's linear or quadratic, but it is clearly linear. No x squared term in sight. So let's go with subtracting 2x from both sides and subtracting 24 from both sides to get x equals negative 28. Is that right? Seem okay? Not the solution I was expecting. Now, if I wanted to check this graphically, that would be a real challenge to find a solution of negative 28. That's not typically what I get when I solve rational equations like this. Now it's in the domain, so if a mistake has not been made, it's not, what were the bad values of x? It's not positive 2, it's not negative 3. So should be all right. But I don't know if I can leave this one alone. That's different from what I usually get. These rational equations, when we graph y equals the left-hand side, y equals the right-hand side, they can have some crazy-looking graphs. We'll spend some quality time in section 3.5 talking about graphs of rational functions, vertical asymptotes, horizontal and slanted asymptotes, and all that kind of business. But right now, we just need to see if we can get the right solution. You think intersection of graphs method or x-intercept method for this one? What would be your preference? Let's try intersection of graphs and see what that does for us. So I'm graphing y equals the left-hand side. And I'm going to graph y equals the right-hand side. Careful to enclose those denominators in parentheses. Now there's a kind of a nice feature that not everybody has access to. So on the one hand, I might hesitate to show it because if you're using the TI-83 Plus, it'll just make you sad that you might not have this feature. But the TI-84 Plus does have kind of a hidden fraction feature that we can explore in a little bit. I think I've got the left-hand side okay, and the right-hand side seems all right. Well, I could start in the standard viewing window. I'm going to zoom 6. I know, since I've already solved this algebraically and come up with negative 28. Now, if you have one of the extra new TI-84 pluses where you can have different colors for your graphs, that's got to be a beautiful thing because it's really kind of difficult to tell which one is which where I'm looking at this. So I'm going to have maybe some calculator envy if I see your calculator and you've got different colors there. So it's kind of hard to tell what's going on. But I'm going to set the viewing window with the x min at negative 40. Just have to go as far to the left as negative 28 if I'm going to get the calculator to concur with my finding here. But negative 40, and set the x scale to 10. So we've got negative 40, negative 30, negative 20, negative 10, 0, 10. And graph it. Both of these graphs, when we get to section 3.5, what we'll see is the one on the left as well as the one on the right, they both, I want to say, I'd really kind of have to add the two rational expressions together on the left. Pretty sure they both have y equals 0 as a horizontal asymptote. That is, if I press trace and move out to the left, like that, both of these are going to approach 0. So the graphs just kind of get buried in the x-axis. Let's do second calc 5 and see if it finds negative 28. Second calc intersect. Enter first curve, enter second curve. If I'm guessing at negative 30, that's probably as good as anything. Enter. Wow. Now it's interesting that the y value is as far away from 0. Maybe it's not that far away from 0. I wonder if the calculator is putting that into scientific. It's not the 0 method. So what we're saying is if we substitute negative 28 for x on the left-hand side, we get negative 0.08. Okay, that kind of makes sense to me. And if we substitute negative 28 for x on the right-hand side, we get 0.08. We could confirm that for the right-hand side pretty quickly. 2 divided by the quantity, negative 28 plus 3. Are you thinking that's going to be negative 0.08? Yeah. Now the other one would take more work. 15 divided by what? Ouch. Negative 28 in parentheses, quantity squared, minus, acting like I've got all the time in the world here. Minus 28 minus 6. but hopefully there'll be some value in this. Plus 3 divided by the quantity negative 28 minus 2. Is that going to give us negative 0.08 if I punched it in correctly?
Yes.
Oh, yes. So you take negative 28, you plug it in the left-hand side, you get negative 0.08. You plug in the right-hand side, you get negative 0.08. You get the same thing on both sides, so it makes it a true statement. So negative 28 does appear to be the solution here. So that's it. That confirms it graphically. Oh, fun fraction feature on the new TI-84 Plus operating system. If your TI-84 Plus is not more than a couple years old, probably it does this, but I don't know how you would tell other than seeing in the owner's manual. If you press alpha, see the green alpha button, and then you press y equals, alpha y equals, you get this fraction menu. The n divided by d, I've got to assume that means numerator divided by the denominator. You might experiment with some of these other fraction features and see what's happening there. If you just press 1, though, you can type like 5 in the numerator. You can type 10 in the denominator, or whatever. You can do this when you're graphing a function that involves a fraction as well, and it avoids having to enclose both the numerator and denominator in parentheses when you do this. So it could save you a few steps, maybe a careless mistake here and there. Not something available to TI-83 Plus users, as far as I know, unless they've started to put the new operating system on the TI-83 Pluses as well, if it's a brand new TI-83 Plus. But it is available on most, possibly not all, but most TI-84 Pluses. Do we have one more of these? I think maybe. Example 7. Example 7, I'm hoping this is going to illustrate what happens when a bad value of x creeps into the solution set. We are about to find out. We don't need to factor the denominators. We have an x minus 1, we have an x, we have another x minus 1. The least common multiple of x minus 1, x, and x minus 1 must have a factor of x minus 1 and must have a factor of x, because there they are. Those are some prime polynomial factors that show up there. But if it has those two, that's good enough. That's divisible by x minus 1, that's divisible by x, that's divisible by x minus 1. So if we multiply both sides by x times x minus 1, we'll have it. So x times x minus 1 times the left-hand side, x plus 3 over x minus 1, plus x plus 5 over x, oops, equals, let's see, I want to go with x times x minus 1 times the right-hand side. And the right-hand side is 3x plus 1 over x minus 1. On the right-hand side, because there's just the one fraction in parentheses, you could go ahead and divide out the common factor of x minus 1. On the left-hand side, it needs to wait. Distribute the x times x minus 1 across the parentheses. So it gets multiplied by x plus 3 over x minus 1. And then it also gets multiplied by x plus 5 over x I'll go ahead and write x times the quantity 3x plus 1 on the right-hand side. The x minus 1's divide out. On the left, let's divide out the factors that remain in those denominators. And I was hoping to, be consistent in the coloring there. No special reason why x plus 5 over x needs to be in red. I meant to put that in blue. Nonetheless, let's divide out the x minus 1's there and get x times x plus 3. And let's divide out the x's and get x minus 1 times x plus 5. And although there's still a good bit of simplifying to do on the left, I'll go ahead and And simplify the right-hand side, 3x squared plus x. The right-hand side is going to possibly go to sleep here. Nothing much to do there for a while. 2 or 3 things need to go on the left. We need to clear the parentheses, x squared plus 3x. FOIL method here. X squared plus 5x minus 1x. That's plus 4x minus 5 equals 3x squared plus x. I guess just one more step, we'll get the left-hand side simplified. Combine like terms, there are a couple of x squared terms. So 2x squared, a couple of x terms, 3x plus 4x equals 7x, and minus 5. Fractions gone, parentheses cleared, like terms combined. Is it linear or is it quadratic? It is quadratic. So the plan is get 0 on one side. And I don't know. You want to get 0 on the left?
Yeah.
I think I do too. So if we subtract 2x squared from both sides and subtract 7x from both sides and add 5 to both sides, we get 0 on the left equals x squared minus 6x plus 5. Wow. That is factorable, isn't it? If so, we couldn't have asked for a much easier one to factor. 0 equals, need an x and an x, and a 1 and a 5 and a minus and a minus. There just aren't any other options to try to factor that. So by inspection, well, never mind the inspection. We'll just set them both equal to 0 using the 0 factor property. And by solving each resulting equation, we get x equals 1 or x equals 5. Are both of those numbers in the domain? I didn't even stop and check and see what restrictions there would be on the domain. I can't believe I didn't do that. 1 is bad, isn't it? Domain, x is not allowed to be 1. X is not allowed to be 0 because those numbers make the denominators equal to 0. No way those could possibly satisfy that equation. So the 1 is bad. After all that work, the 1 does have to be kicked out, but the 5 remains. So the 5 appears to be a valid solution to this. You could confirm it graphically if you want to. I don't think I have the time to do that. But I'm going to say the solution set includes the 5 and only the 5. Let's see if we can solve a radical equation or two. Before example 8, I want to do an example 7.5. I do this in my intermediate algebra class, and typically in college algebra, I just don't have it in my notes this semester. Example 7.5. Maybe I should call it some not so radical equations. Not so radical equations. Got a half dozen of them here. A part. So the directions are solve, i.e. Find the solution set to each equation. That's what solve means. Find the solution set. X equals 5. Can we solve this? It kind of looks solved, doesn't it? We can write down the solution set, which includes only what number? 5. There we go. I said it was not so radical. Kind of nice there. B. 2x equals 10. Actually, didn't mean to do that one next, but I guess I can. 2x equals 10. The solution set certainly is 5. 2 times 5 is 10. 2 times anything else is not 10. So C, I better go with x over 2 equals 2.5. What is the solution set? Take 5 and divide it by 2, you get 2.5. Take anything else divided by 2, you don't get 2.5. 5 is the only solution to this equation. The D part, x plus 2 equals 7. But I don't think we need Siri's help on this one, although I'm sure she would be quite capable of handling this. X plus 2 equals 7. Siri is surprisingly good at math. I don't know. X plus 2 equals 7. 5, yes. If you take 5 and add 2, you get 7. Take anything else and add 2, you don't get 7. E. X minus 2 equals 3. What works here? 5 works. Nothing else works. 5 minus 2 is 3. Anything else minus 2 does not equal 3. And then the kicker. X squared equals 25. 5 squared is 25.
-5.
And -5. There we go. Okay. So square the 5, get 25. Square -5, also get 25. So an extra solution to this. When we're solving equations, various things we do to start with something more complicated and work our way towards something less complicated. What I've done is kind of the reverse of this. I've started with something very simple, x equals 5, and in the B, C, D, E, and F parts, deliberately messed it up by doing something to both sides that typically we do to try to simplify. Now, when we, let's see, from x equals 5 to 2x equals 10, imagine starting with x equals 5 and doing something to both sides. What might I have done to both sides of x equals 5 to arrive at 2x equals 10? I multiplied both sides by 2. Now, a lot of times you multiply both sides by 2, it makes the equation a little nicer, not in this case. But we do that, and we want to do two things. We want to make the equation a little nicer, and we also want to make sure that the solution set to the equation that results is the same as the solution set to the equation that we started with. It doesn't help to do something to both sides to make it look nicer if we lose solutions, or if we have a different solution set to the new equation than what started. We want to preserve the solution set. That's called having an equivalent equation. Two equations are equivalent if they have exactly the same solution set. Multiplying both sides by 2 is guaranteed to give you an equivalent equation. From x equals 5 to x over 2 equals 2.5, what did I do to both sides? Divide both sides by 2. Dividing both sides by 2, any positive number, any negative number? Now, we never want to divide both sides by 0. That would be crazy. But if we divide both sides by the same positive or negative number, it's guaranteed to produce an equivalent equation. From here to there, what did I do? Added 2 to both sides. That also, adding 2 to both sides or subtracting 2. Any positive number, any negative number to both sides, guaranteed to produce an equivalent equation. We do that sometimes to isolate one of the variables or isolate one of the terms. We add the same quantity to both sides, we subtract the same quantity from both sides. Now the F part is different. Did something to both sides. What did I do to both sides there? Squared both sides. Now when solving a radical equation, particularly a square root radical equation, it's going to be helpful to square both sides. If we have a square root radical and want the thing to go away, we're going to want to square both sides. But we have to realize when we do that, it's not guaranteed to produce an equivalent equation. We started with an equation, the solution set contained only a 5. X equals 5. 5 is the only thing that satisfies that. We squared both sides. Good news, bad news. The good news is that we did not lose the 5. That's still a solution to the new equation. It wouldn't really ever make sense to do something, perform some operation on both sides of an equation that would cause us potentially to lose a solution, because we just wouldn't have any way to figure out what might have been lost in the process and how to get it back. So squaring both sides doesn't cause us to lose anything, but bad news, or caution, warning, it might give us something new when we square both sides. -5 is not a solution to x equals 5, but after squaring both sides, all of a sudden, it's in the solution set. We call this an extraneous solution, and in fact, I don't know why I didn't define extraneous solution in the previous example, because that's exactly what the 1 was. We didn't make a mistake as far as I could tell. We did everything right, but 1 was extraneous because it was not in the domain. It's a solution to this equation and most of the ones that we dealt with, but it's not a solution to the original. So that's also an example of an extraneous solution. So, word to the wise here when we're solving these radical equations. Whenever we're solving an equation and we have an occasion to square both sides, it's okay to do that. We just have to keep in mind at the very end, it's possible there are numbers in that solution set that do not satisfy the original equation. So it just means we have to check them. It's not enough just to have mad algebra skills where we just don't make a mistake ever. We can do everything right and still get numbers that don't belong in the solution set. We have to check the solutions as part of the problem solving process. So let's give that a go with example 8. Example 8, solve the radical equation. Now, basic steps here: to get rid of the radical, we're going to need to square both sides, but it only really completely gets rid of the radical if that radical is all by itself. If I've got a radical plus 7 or something like that, squaring that left-hand side is going to reposition the radical a little bit, but it's not going to make it go away. So step 1 is to isolate the radical that we wish to get rid of. So I'm going to subtract 7 from both sides. -7 minus 7, and we get the square root of 3x minus 6 equals 2x minus 7. Simple enough, but that isolates the left-hand side, the radical on the left-hand side, and so that when we square both sides, squaring the square root of 3x minus 6 will just leave us with 3x minus 6. Squaring the 2x minus 7, we have to be careful, but we can FOIL or use the formula for squaring a binomial, and we should be good. So we square the left-hand side, we square the right-hand side. Oops, there we go. The square of the square root is the radicand. And 2x minus 7 quantity squared, certainly. We get a 4x squared. Certainly. We get a 49. And we certainly don't want to leave out that middle term. What is that middle term? Minus, well, there are a couple of minus 14x's, aren't there? There's a minus 14x for the O, another minus 14x for the I. So we get 2 of those for a total of minus 28x. Twice the product of the 2 terms for the middle term when squaring a binomial. Okay. Well, let's see, there weren't any fractions. We got the radicals are gone. Not a lot in the way of simplifying. A little bit. I guess we did need to simplify the right-hand side. No like terms to combine. Is this resulting equation linear or is it quadratic?
Quadratic.
It is quadratic. So we're thinking we're hoping maybe we can factor this. So let's go with the 0 on the left. Subtract 3x, subtract 3x, add 6, add 6. When we do that, we'll get 0 equals 4x squared minus 31x plus 54. No, what's 49 plus 6? 55. There we go. So much for those mad algebra skills, or mad arithmetic skills. I don't know. Are you thinking you want to try to factor this? Maybe not. I mean, if we wanted to use the AC method, I think I could get it done. But if in practice your go-to method is the quadratic formula, that might be what we want to do right here. And then once we get the answer, if the solutions are rational, we can say, oh, by the way, it would have factored like this. So a quick show of hands, who would prefer that I just go directly to the quadratic formula here? All right. Anybody feel strongly, you ought to just try to factor it? Yes? Anybody else?
We're factoring 31.
Factor?
1 and 31.
Well, you don't need factors of 31, though. You need
If you AC it, though.
If you AC it, you need factors of whatever 4 times 55 is. 220, maybe? And we'll look at that after the fact and see. But let's approach this with the quadratic formula, and then we'll say, oh, by the way, yeah, it would have factored nicely if only we'd taken the time to do it. The opposite of negative 31, plus or minus the square root of negative 31 quantity squared, minus 4 times another 4 times 55, all over 2 times 4. So it's 31, plus or minus the square root of, I want to say that's 961. So 961 minus whatever 16 times 55 is, 880. Okay, seeming not quite so bad. X equals 31 plus or minus the square root of 81 all over 8. 31 plus or minus 9 all over 8. Again, for the third time, I think, this semester. Quick show of hands. Who knows what 31 plus 9 is? Who knows what 31 minus 9 is? Absolutely. So we don't put a box around this and walk away from it. We write it as two separate expressions, one with a plus, one with a minus, simplify both of them, and then we'll need to check them and make sure they work. X equals 31 plus 9, quantity over 8. Or X equals 31 minus 9, quantity over 8. That's 40 over 8. Or 22 over 8. Maybe, possibly. Do I know what 31 minus 9 is? Yes. Okay, good. X equals 5. Or X equals 11/4. Those two possibilities. So, armed with this information, we could go back here and say, since we know that 5 is a 0 of this expression, x minus 5 was probably one of those factors, and since we know that 11/4 is a 0, we could say x minus 11/4, but I'm thinking probably it would have been 4x minus 11. Looks so simple. When we know what the factors are, it's like, oh yeah, clearly that's what it would have been. X minus 5 times 4x minus 11, you'd have 11x minus 20x. 11x minus 20x when you FOIL that, which would have given us back the minus 31x. So it's easier to factor something if you know the answer ahead of time. Let's check x equals 5. We want to check. Let's go back to the original equation. Check. X equals 5. Square root of 3 times 5 minus 6 plus 7. We're wondering, does that equal whatever 2 times 5 is? So this is square root of, looks like 9. 15 minus 6 is 9, plus 7. Wanting to know if that's equal to 10. Now, square root of 9, we know 9 has 2 square roots. Positive 3 and negative 3. Either one of them, when you square it, we get 9, and they're both officially called square roots of 9. Positive 3 and negative 3. However, when we write that radical sign, radical 9, we're only talking about the positive square root of 9. The principal square root of 9, we call it. So I don't have the luxury of choosing the positive 3 or the negative 3, whichever one might suit me better in the given circumstance. I've got to write 3. Turns out that's the one I actually need in this case, because 3 plus 7 does equal 10, and it checks out. So the 5 is good. At some point, we will make sure to include the 5. Another one with, how many equations is this in a row where the solution includes a 5? A bunch of them. Let's see if the 11/4 belongs as well. So let's check x equals 11/4. A little fraction action going on here. The square root of 3 times 11/4 minus 6. If we add 7 to that, does that equal whatever 2 times 11/4 is? Here, this is the square root of 33/4 minus, how many fourths is 6? 24/4 plus 7. Does that give us 11/2? 22/4 or 11/2 on the right-hand side. On the left, this is the square root of 9/4. Going to add 7 to that and see if we get 11/2. 9/4 has 2 square roots, 3 halves and negative 3 halves, but we must write 3 halves. 7 is how many halves? 14 halves. See, if we could have gotten by with writing the negative 3 halves, we could make this work, right? Negative 3 halves plus 14 halves is 11/2, but that's not allowed. Radical 9/4 means 3 halves. So we get 17 halves, 3 halves plus 14 halves, 17 halves on the left, 11/2 on the right, and that is not a true statement. So we've got to scratch the 11/4. It's extraneous. And the 5 is all that we need in the solution set. That's it. Just the 5. How do you feel about this one? Have you solved an equation like this before somewhere? We do these. Intermediate algebra to some extent. Yes.
Is there one way you could figure that out by checking it?
The factoring?
If 11/2
Oh,
was the solution.
yeah. In my experience, yes. It seems like there ought to be some direct procedure that if we follow that procedure carefully, we're not gonna have. It's like the what is it? 11/4. If you're walking through grass, these little burrs that cling to your shoelaces and are really painful to remove. That's really what the 11/4 is. We're following the path as closely as we can, but we get these extraneous solutions that just kind of creep in and attach themselves to the solution set. And we have to get a pair of needle nose pliers or whatever and get them out. I just don't know of a direct method, other than maybe a graphical method. If you graph it, you can actually see what's going on, but not this, as far as I know. It's a good question. I don't have a good answer to it, I don't think, other than I don't know. Yeah. And, some good additional practice problems. The G part, just for reference here, is a fun kind of problem. I mean, you can just looking at it, you can see how much fun it is, right? That's got to be a blast working through that. The one on the test, radical equation, I'm going to restrict it to a 1 radical equation rather than a 2 radical equation, and square roots rather than cube roots. Cube roots actually are easier. Cube root equations come in my opinion, 2 flavors. One where it's just ridiculously simple, and another one ridiculously impossible. And I don't want to give you ridiculously simple. I think the square root equation, like we did today, is kind of just right. one radical, but yet you have to square a binomial. You get two solutions with a quadratic, but one of them doesn't work. That's kind of in the sweet spot of what I would expect college algebra students to be able to work through. So G and H, if you like a challenge, some interesting things going on there. You have to square both sides a total of twice to get both radicals completely to go away. So it would be good practice. And I don't know, Alex might give you one with two radicals, although I kind of doubt it. I think that I may have eliminated the two radical practice problems from Alex. So I think that's all I want to say about radical equations. In the remaining 6 minutes and change, let's look at least one of these equations that is quadratic in form. Maybe the B part, fresh off the discussion of extraneous solutions. I think we may run into one more that involves an extraneous solution. 2x to the 1/2 power minus x to the 1/4 power minus 1. It's quadratic in form because one of the exponents, basically you've got your three terms. You've got x raised to 1 power, x raised to another power, then a constant term. That's what you see with a quadratic equation. With a quadratic equation, you've got x to the 2nd power, x to the 1st power. Well, this is similar to that in the regard that you've got x raised to these two different powers, and one of the powers is exactly twice the other power. That's what we need. If we had a 1/3 and a 1/4, it really wouldn't work for us, x to the 1/3 power, x to the 1/4 power, because 1/3 is not exactly twice 1/4. We need one of them. I mean, we could have, this could have been 2x to the 6th power minus x to the 3rd power minus 1 equals 0. That would be quadratic in form because the 6 is exactly twice the 3. We could have had 2x to the 14th power minus x to the 7th power minus 1 equals 0. That would have worked, and it would have been quadratic in form. We just need one of the exponents on the x to 1 power, x to half of that power on the other term. So these are some examples there of other types of equations that are quadratic in form. But what we want to do is do a substitution and rewrite this as an actual quadratic equation. What we do is we let u equal x to the power that's half of the other power. If it's a quadratic equation, you've got an x to the 1 and an x to the 2. Well, we want our u here to be x to the, whichever of these two exponents is half of the other one. Well, you've got a 1/2 and a 1/4. Which of them is half of the other one? The 1/4 is the one that's half of half. So let u equal x to the 1/4. Then u squared is x to the 1/4 squared. U squared is basically going to be the other one. So u squared is going to be x to the 1/2. So we can pick up the x to the 1/2 and replace it with u squared. We can pick up the x to the 1/4 and replace it with u. And all of a sudden we have a true quadratic equation in the variable u. And we solve it like we solve quadratic equations. We say, well, I think I can factor this, 2u and a u and a minus 1 with the u and a plus 1 with the 2u. Get a minus 2u plus 1u is minus u in the middle, negative 1 on the end, and 2u squared in front. I think this is the factorization that works here. We can find values of u by using the zero factor property. 2u plus 1 equals 0, or u minus 1 equals 0. And then skipping a step or two, we can say u equals negative 1/2 or u equals 1. Let me take a quick breath. How do you feel about u equals negative 1/2 there? Subtract 1 from both sides, divide both sides by 2. U ends up being negative 1/2. Okay. Not solutions to the equation. We want to find the values of x that make this thing true, but they get us closer to it because instead of now having to solve this fractional exponent equation, it's a couple of linear equations. Instead of the quadratic, it's a couple of linear equations, but we've got to take the x to the 1/4 and put it back. So let's bring it over here. u was equal to x to the 1/4, so we say x to the 1/4 equals negative 1/2, or x to the 1/4 equals 1. Maybe that's the pivotal step there. That's tough with just 2 minutes left to go to do a pivotal step, but there it is. We want to come back and say, okay, it's not really about what u is, it's about what x is. X to the 1/4, and then we complete this by raising both sides to the 4th power. We want x to the 1st power, not x to the 1/4 power. So we raise both sides to the 4th power in each of these equations, and we get x equals 1/16, I think. Negative 1/2 times negative 1/2 times negative 1/2 times negative 1/2, I think, is positive 1/16, or x equals 1. And in the minute or two that remains, we might actually be able to check this. Squaring both sides, we have to check. We also have to check if we raise both sides to the 4th power. It's an even power, so it could generate extraneous solutions. I think checking x equals negative, what was it? No, x equals 1/16 is not going to work out. 2 times 1/16 to the 1/2 minus 1/16 to the 1/4 minus 1. Is it going to give us 0? How do you take 1/16 and raise it? How do you take anything and raise it to the 1/2 power? What do you do? It's the square root of 1/16. How do you raise something to the 1/4 power? It is the 4th root of that number. So what's the square root of 1/16? 1/4. And the 4th root of 1/16? 1/2. I don't think this works. This is 1/2 minus 1/2 minus 1. I think that's not 0. I think had we had the luxury of choosing positive 1/2 for the 4th root of 16, we could have gotten there, but we did not have, well, if we had the luxury of choosing negative 1/2, rather, for the 4th root of 1/16, we could have gotten there, but we didn't. I think, and the clock's going to strike 9:15 here in a moment, but if we check x equals 1, 2 times 1 to the 1/2 minus 1 to the 1/4 minus 1 equals 0. I think it's good. So what's that? 1? It is 1. So 1 satisfies this. The 1/16 does not. So the 1/16 is extraneous. I think I've done the B part of this, but not the A part. Did I skip over the A part? Anybody remember?
Yes.
I did skip over the A part. Let's look at the A part and then go on to the next section. No fractional exponents to contend with in example 9a, but there is the matter of substitution. This is pretty straightforward once we do the substitution. If you can look and kind of see what's going on here, you could actually factor this probably, realizing that it's quadratic in form without formally setting u to be x squared. But, and if you want to do that, that's fine. I don't have to see the letter u show up in this example for you to get full credit for it. But if it's not obvious, the only thing I would expect you to be able to look at and see is that there are 3 terms, and there are a couple of them with x's in them to different powers, and one of the powers is twice the other power, and the other term is a constant term. That's what you recognize, and when that happens, it's quadratic in form, and you let u equal x raised to the power that's half of the other power. Now, I would say, well, just let u equal the one in the middle term. But what if the terms are rearranged? Who knows what's in the middle? There's x to one power, there's x to another power. One of those powers is half of the other power. Let u equal that, x to the second power in this case. If that's the case, then what's u squared going to equal? X to the 4th. Yes, it's x squared So that's x to the fourth. We're multiplying those exponents there. 2 times 2 to give us 4. Then we pick up the x to the fourth and replace it with u squared. And we pick up the x squared and replace it with u. And then we've got an official quadratic equation in the variable u. And you could apply the quadratic formula if you'd like to, because this does, if I planned it right, factor. I'd like to try that first. What two integers can you multiply together to get 100 and add together to get negative 29?
25 and 4.
Yes, so u minus 25 and u minus 4, since we need the negative 29 u in the middle. We have minuses for both of them. Apply the zero factor property. Or set each factor equal to 0. And then by inspection, or by adding 25 to both sides, we can see that u equals 25 satisfies the first one. And by adding 4 to both sides, we can see u equals 4 satisfies the second one. We find the values of u, and that's good. That's a big step in the right direction. It's not the final answer, though. If we substitute 25 or 4 for these x's, they're not going to work. But if we substitute x squared for the u in both places, now that the equation is easier. If you've got this, you might not want an x to the fourth power. That's a more complicated looking equation. You'd rather have u to the second power, just plain old u. But once you get to the point where it's just u equals 25 or u equals 4, you don't mind picking that u back up and putting the x squared in place of the u, because those are simpler. And now that they're simpler, we can put the x's back in and apply what? The square root property of equations. Think in, take the square root of both sides, but really, you're just observing that if x can be squared to get 25, x is either the positive or negative square root of 25. X can be either the positive or negative square root of 4. Since 25 and 4 are both really nice perfect squares. X could be plus or minus 5. X could be plus or minus 2. And at no point did we square both sides. In the B part of this that we worked at the end of class last time, both sides were squared, or both sides maybe were raised to the fourth power at some point, and it resulted in extraneous solutions. But that didn't happen in this case, so all 4 of these are going to be good. 2, negative 2, 5, negative 5, 4 solutions to this 4th degree polynomial equation. And if you graph it, you can see 4 x-intercepts. If you just graph y equals the left-hand side, you can see all 4 x-intercepts, and they'll intersect the x-axis very clearly at negative 5, negative 2, positive 2, positive 5, if you look at it there.